Hello, everyone. My name is Tomasz Zawadzki. I'm a cloud software engineer at Intel, and I'm fulfilling the role of SPDK core maintainer in the project.
My name is Jim Harris. I'm a principal software engineer, also in Intel's data platforms group. I'm also an SPDK core maintainer. So Tomek and I would like to introduce our topic today, SPDK Schedulers, doing power savings in pulled mode applications. So first we'll start off with the usual notices and disclaimers. We'll let you read that offline more later if you're so interested. But let's go ahead and move forward to the good stuff. So first, an SPDK overview. So I'm sure a lot of you are already familiar with SPDK. If not, there's some other talks that you can go back and look at, SDC talks at other conferences. But just to give a little bit of an overview, just real quick today before we dive into our topic, SPDK is a framework for building high performance storage applications. And you see a lot of blocks there in that diagram. They really represent sets of drivers and libraries, but also SPDK includes fully functional storage target applications. And that's actually the basis for what we're going to talk about today is how to get power savings from those applications. SPDK uses a user space pulled mode programming model. One of the key parts of SPDK is it's not just an open source project, but it is an open source community. If you go out to our website, spdk.io, you can find a bunch of different channels to reach out. If you've got more questions on the talk we have today or just SPDK in general, please feel free to reach out there. So let's go ahead and talk a little bit about the SPDK threading model. So, we talked a lot. I talked just briefly there about how we use a pulled mode programming model in SPDK. And so I want to talk a little bit about what that threading model looks like, because it's really lays the basis for the scheduler stuff that Tomek's going to talk about later in our talk. So when you look at an SPDK application, it has, you set it up to run on a certain number of cores. And so this, the example we're showing here today is we're running the SPDK application on 4 cores. And we call an SPDK reactor on each of these CPU cores. And this reactor is effectively a pinned POSIX thread. So this is the only thread that only POSIX thread that we run on each of these cores. And these are created by the SPDK application framework. So a little bit about that application framework. The libraries in SPDK are all designed to be integrated into existing applications, existing frameworks, but SPDK does have its own application framework to bring up these threads, to get them running on cores. And so that's what we're going to primarily focus on today. But everything we talk about with SPDK threads today is independent and can be integrated into other application frameworks as well. So these SPDK threads are really it's a lightweight threading abstraction. There is no tie between an SPDK thread and a POSIX thread. By default in SPDK, we typically have one SPDK thread per CPU core. These are created by the top level block storage protocol library. So for example, when the NVMe-oF library is initialized, the NVMe-oF target library, it will by default create one SPDK thread that runs on each CPU core. The other block storage protocols then may create their own SPDK threads to run on those CPU cores. And then at the top layer, the application framework, whether that's SPDK's framework or whether it's some other application framework, is responsible for calling SPDK thread pull on each of those SPDK threads. And that's how those threads get an opportunity to actually do their work. So next, if we look at what SPDK thread pull does. So each of these SPDK threads will execute code from a number of different libraries. So it could be the NVMe-oF target layer. The NVMe-oF target layer may call down into the block device layer. The block device layer may call into SPDK block device modules like the NVMe driver, or maybe CephRBD or libiSCSI. And these libraries will all register SPDK pollers. And these SPDK pollers become associated with the thread that they were registered on. And these pollers are all responsible for polling on something. So it could be an NVMe queue pair. It could be a epoll file descriptor. So for example, in SPDK, we make heavy use of epoll to poll like groups of TCP sockets or CephRBD event FDs. It could be polling on an RDMA completion queue. And the key part here is that every time the framework calls SPDK thread poll, it's going to poll each one of those SPDK pollers. So each SPDK poller is going to get a chance to run to go check for and do some work every time the thread is polled. There is a small exception here. We do have the concept of timed pollers in SPDK, where you can register a poller to run at a specific time interval. So for example, you want this to run every 1 millisecond. So of course, those pollers are only going to run once that millisecond expires. They're not going to execute every time that the thread is polled. The other thing that these threads do is each thread has a message queue. So we make heavy use, it's a shared nothing architecture. So instead of using locks in SPDK, if threads need to communicate, they can send messages to one another. And so that's another thing that SPDK thread poll will do, is when a thread is polled, it will run, basically execute any messages that have been sent to that SPDK thread. Okay, so how do we save power when we're idle, right? So now we have these SPDK reactors running. We have these SPDK threads with their SPDK pollers running in each core. But when everything's idle, all these pollers are doing is just using up CPU cycles. And so, doing this polled mode programming gets us great performance and efficiency when the CPU cores are busy. But what we've been looking at is how do we save CPU cycles when those cores aren't as busy, effectively when they're idle or when they're running, a very, very low IO workload. And so, there's a few potential ways you can do this. There's some ways that some other frameworks like DPDK are looking at. And so we're going to talk about a couple of those, why maybe they don't exactly meet with what we want to do with SPDK, and then we're going to move into the solution, the SPDK scheduler solution that Tomic's really been focusing on. So the first one is interrupt mode. So basically having SPDK threads which can effectively block on events. We actually do have some limited support for this in SPDK. It's restricted to a very small subset of the libraries, though. Today, that doesn't include the NVMe driver. It does not include the NVMe-oF target library. It really only supports libraries that register file descriptors with the SPDK thread, because then we can actually block on like an epoll file descriptor. So the challenge here is to extend this to the rest of SPDK becomes really, really complex. You end up having, multiple layers of nested FD groups. The other challenge is that every single library or module in SPDK then has to support this, right? Because you can't have one, library that requires, polling something without something that they can block on. And so that becomes a challenge. Maybe at some point down the road, SPDK will support that, but that's not the direction that the project is taking right now. So next, on x86, there's some newer instructions in some of the upcoming CPUs for doing monitor and umwait unprivileged. So being able to do these from user space. So for those that are familiar with how these work in the kernel, you can basically set up a monitor address And then you can execute an umwait instruction, and it'll basically put that CPU thread, that CPU core, into a deeper, power state. But once there's a write to that monitored address, it will wake it up. And so these instructions are, once these are available, user space processes can take this same approach. And this works really, really, really well when you have one thread that's pulling on one hardware queue. And so we see this a lot in packet processing applications. So for example, in DPDK, where you've got maybe a relatively small number of hardware queues, receive queues that you're receiving packets for, and you can actually do a monitor on the next descriptor that's in the buffer ring. But the challenge for SPDK is that we are typically pulling many hardware queues from one thread. So for example, in the case of like NVMe, where we may have a whole lot of NVMe SSDs in the system, but certainly when you're pulling kernel TCP sockets, not only is it not a hardware queue, but you've got potentially tens or hundreds or even thousands of kernel TCP sockets that you're wanting to observe events on, and the umonitor having that single address range doesn't really fit for that use case. So the third option is, what happens if we could move these SPDK threads, right? So, in this example here, we show that the SPDK threads that were running on cores 1 and 3 are being moved to cores 0 and 2. And so if we can do this, it allows us to put a CPU core to sleep, right? Because now cores 1 and 3, they no longer have any SPDK threads that are running. But then we also know that those threads are going to continue to be pulled on the cores that they've been moved to. And fortunately, this is very, very well supported by the SPDK threading model. So when those threads allocate resources, so for example, those pollers allocate an NVMe queue pair, or they create a file descriptor for, they have file descriptor for a TCP socket, we only ever pull or touch those resources on that SPDK thread. So as long as we continue with that threading model where we only touch those resources on that thread, it doesn't really matter what core we're doing it on, we're still going to be thread safe. And so with that being said, I'm going to turn it over to Tomek, and he's going to go into SPDK schedulers and how they can build on top of this.
Thank you, Jim. So everyone, Jim described how the SPDK threading model, particularly threading library, works together with event framework to allow for moving of the threads. But the actual interaction happens with the scheduling framework in a very similar manner. So I would like to describe how the scheduling phases occur during a single scheduling occurrence. One important part to remember is that whenever scheduling is in progress, is happening, the reactors, the cores, still pull the SPDK threads. There's no stop of the operation during the scheduling. So scheduling is performed on an interval called scheduling period, which is set by the user whenever he enables a particular schedule. When the timer expires, gather matrix, the first phase, starts. In similar fashion first, it has to be mentioned that in similar fashion to SPDK threads sending messages between each other, so do reactors by sending events, which is an abstraction on the event framework level. And exactly this mechanism is used to send an events between different cores to execute the gather matrix function. Anytime an SPDK thread is pulled, the result of the pull, as well as the time of its execution, is gathered. This makes it possible for gather matrix to collect that information on per thread as well as per call basis. The most important data here is the number of cycles spent executing the SPDK thread, and it's put into two types of categories for threads that did the work, which is the busy TSC, as well as those that ultimately didn't, the idle TSC. This information is available for both last scheduling period, as well as a total of a lifetime of a thread. Similar data, cumulative data for particular core is available as well. And there's a couple of other parts to the structure here. It's the SPDK threads core, that is, SPDK threads L-core assignment, as well as data for what current core mode is, whether it was put to sleep or not. So once gather metrics go over all the reactors, the data is the input to the balance function, as well it will be the output of that function. Second phase of the scheduling is the decision point, where an action can be taken based on the previously gathered information. So schedulers can decide to change the SPDK threads core assignment, can opt to put a core to sleep if no SPDK threads are present on that core, as well as modify the core frequency using SPDK Governor. More on this on the next slide. So the logic behind the balance function is implemented by pluggable SPDK schedulers. On the right is the interface that has to be implemented by such schedulers. Besides that, the SPDK scheduler register macro has to be called to make the event framework aware of the new scheduler. After that point, a user can switch between different implementations in runtime using the framework set scheduler RPC. And optionally, a scheduling period, a custom scheduling period can be provided. At this time, one such scheduler is called dynamic, and it has been implemented. Later in the presentation, I'll go over the goals of the dynamic scheduler, as well as the results of the CPU utilization comparison against the static SPDK thread assignment. As I mentioned during the balance call, schedulers can optionally use what is called SPDK Governors. This is another abstraction that allows to change the frequency of a particular CPU core used by the application, thus reducing the power used by that very core. Right now, SPDK provides governor called DPDK Governor based on top of DPDK's RT power library. It's possible, similar to the schedulers, to implement new kinds of SPDK governors. And similarly, once a particular governor is registered within the event framework, any scheduler can enable it during its initialization. And finally, this concludes the balance function implemented in the scheduler. And now the operation moves back to the event framework, where the output from the balance function, meaning the core info and thread info structures, are fed back into the event framework. So two actions are taken based on that data, on this balance output data, changing the core mode, meaning putting a core to sleep or waking it up. This action is performed on each core, depending on the output from the balance. Another is marking SPDK thread for move to a different reactor. This action is only performed on the main core, because once SPDK thread is marked for the move, the reactor which currently has the thread assigned is responsible for first stopping stop of the polling on that particular reactor, as well as sending an event to the destination reactor to start polling it there. After that, the scheduling phases are complete, And next one will start on the next, once the scheduling period expires. Before the addition of the scheduling framework, the threads were assigned a particular core and remained there for the application's lifetime. The static thread assignment is now part of the static scheduler, which remains the default. But in addition to that, as of the latest SPDK releases, users can enable dynamic scheduler via RPC. Besides adding the scheduler framework, the dynamic scheduler has been a focus for us to prove out the concept. This particular scheduler's goal was to save power when possible, but not at the cost of the performance. Dynamic scheduler will err on the side of caution when consolidating SPDK threads on particular core. Once an SPDK thread becomes active, it will be put on a core that allows for its best utilization, which means either an unused core or the one that is least busy across the application. In every use case, it is possible, in a very active use case, it is possible that no difference would be observed between the dynamic scheduler and static scheduler. Yet, for the cases when particular thread's utilization goes down, it is consolidated with other SPDK threads. And if it's totally idle, it is put directly on the main core. Any core after such move that is left with no SPDK threads is put to sleep to save the power. Finally, the CPU frequency of the main core when its utilization is low is reduced. And this is the main core is the last remaining core whenever all others are put to sleep. With that said, now let's go over some of the performance and importantly, CPU utilization data for select cases, comparing dynamic scheduler and static thread assignment. SPDK project publishes quarterly performance reports for key components. The following results are performed in similar fashion to the SPDK NVMe-oF TCP report, specifically test case 4, which measures NVMe-oF performance with increasing number of connections. In this case, the NVMe-oF TCP target, one SPDK thread is present in each core, and 30 CPU cores were assigned for the whole application. This is the number always used by the static scheduler and the maximum the dynamic scheduler can use. On the next slide, CPU utilization shown will be measured for the whole system, which means it can exceed the value of 30 CPUs, in part due to, for example, kernel TCP stack processing. To that target, 2 SPDK NVMe-oF TCP initiators are connected, each consisting of 8 NVMe-oF subsystems. FIO SPDK BDEV plugin is used to perform 4K random read workload on each of those NVMe subsystems, where a couple of parameters are scaled. First, the queue depth is scaled to result in higher utilization whenever it is increased for each SPDK thread. Meanwhile, increasing the num jobs parameter in FIO results in higher number of TCP connections being created to handle the I/O generated. This means that the more TCP connections per each SPDK threads are present on the target site whenever that parameter is increased enough. This particular case shows the results when there are 16 NVMe-oF subsystems connected with num jobs set to 1, resulting in total of 16 TCP connections handling the I/O. This, of course, means there are actively 16 SPDK threads being used due to the number of connections. Please note that the line representing thousands of IOPS in both cases are on the same level. That means that no performance was lost switching to dynamic scheduler in this particular case. Meanwhile, comparing the blue and orange bars shows the difference in CPU utilization between the cases. The orange is static scheduler, consuming always at least 30 CPU cores as configured. Meanwhile, blue bars represent dynamic scheduler, collapsing SPDK threads to minimal set of CPU cores, depending on the I/O load. When QDEP 8, with QDEP 8, the load is so low that multiple SPDK threads run on the same CPU core, and the other CPU cores are put to rest, resulting in around 10 CPU being utilized across the during the test case. For very high I/O load, in case of QDEP 128, each connection needs to be processed on the separate core, resulting in all of the 16 threads occupying a separate CPU core. The rest of the CPU cores are not used due to the low connection count, so they are put to sleep. That said, before going to the next case with increased number of connections, let's discuss some of the underlying mechanism behind the NVMe-oF SPDK polars, QPers, and TCP connections. As previously mentioned by Jim, SPDK polars in NVMe-oF TCP poll and ePOL FD. That file description corresponds to a group of multiple TCP sockets. Each TCP socket represents an NVMe-oF QPer, and assigning the NVMe-oF QPers to NVMe-oF poll groups is done in a round-robin fashion. There is no guarantee that QPers will be distributed evenly across SPDK threads, as well as a single SPDK thread can consist of multiple QPers with varying amount of activity. Another is QPers connecting and then disconnecting, resulting in uneven number of QPers for each SPDK threads. Finally, another one is the initiator side can spread the load across multiple QPers, thus sometimes playing against the scheduler detecting the load on the target side. Poll group mechanism has worked great in the past for the static scheduler, yet with dynamic scheduling in use, it can diminish the benefits of such scheduling. The next case shows the results when there are 16 NVMe subsystems connected with num jobs set to 4, resulting in total of 64 TCP connections handling the I/O, meaning all of the 30 SPDK threads are actively being used. Again, the line representing thousands of IOPS being in both cases are on the same level. That means no performance was lost again. Meanwhile, comparing the blue and orange bars shows the difference in the CPU utilization, pointing on the low I/O load with QDEP 8, the SPDK threads were collapsed to around 22 cores, but going to 64 QDEP results in capping out the CPU utilization similar to the static scheduler. All across those cases, some of the cycles are spent on calling ePOL in each of the SPDK threads. Better or possibly dynamic organization of NVMe-oF poll groups across the SPDK threads would allow to further decrease the CPU utilization in many of those cases. So having said that, let's go over some of the key highlights from this presentation, as well as next steps for the SPDK event and scheduler frameworks. Poll mode applications require special handling to save power and CPU cycles when idle. SPDK event framework now allows for moving idle SPDK threads to put cores to sleep, thus saving power. Pluggable SPDK scheduler framework is provided to define when and where SPDK threads should be moved. SPDK Dynamic Scheduler was added. It consolidates SPDK threads on minimal set of calls and puts remaining calls to sleep. Even seeing the progress we've made so far, the work does not end here. The dynamic scheduler logic for balancing could use further improvements. For example, one of the requests we got was to provide a tweakable values to the user to allow better suitability for each of the use cases being run. The cost of multiple poll groups on a single core needs to be addressed to further reduce the CPU utilization. And right now, Dynamic Scheduler is using DPDK Governor, only scales the frequency of the main core. This could be improved by changing frequencies of other cores depending on their load too. Finally, Dynamic Scheduler prioritizes core selection based on their L core number, but the selection could take into account other factors such as umonitor, hyperthreading, or high-frequency cores. Thank you, everyone, for attending this session and hearing about our learnings while implementing SPDK scheduling.
Thank you.
And